we begin the class lecture will just pertain to the due dates. So as I mentioned last time in class, there's only 3 due dates you really have to worry about. One of them is counting principles, the stuff we finished last time in class, that's due tonight. So that homework is due tonight, and the corresponding quiz is due on Friday. That's 2 of the 3 assignments. The third one is the workbook assignment that I assigned last time, workbook number 3. So this is also due on Friday, and that's everything you need to worry about as far as this week goes. Stuff on probability, we'll focus on that next week. So besides for that, does anyone have any questions about anything before we get started on the new section? If not, let's go ahead and start off with the new material on probability. So probability, so really the previous 2 sections have slowly been working us towards this idea of probability. We started off talking about sets, which were this formal collection of objects. And then we started counting the number of items in a set. That's ultimately what we've been doing in the counting section. And so probability is going to seem very similar to the counting section that we did last section. But what we're going to do is we're going to look at ratios of things that we count. And these ratios will give us a probability. So this probability, in other words, the likelihood of something happening out of the total number of occurrences. And so you're going to see a lot of resemblance between this section and the last section. But just to discuss some of the terminology, a sample space that's interesting. Well, seems like the pen doesn't work. Fantastic. Well, all right, 1 second. Technical difficulties. Pen's not working. Okay. Works there. Okay. Okay. Never mind. Guess it works now. Some technology, great. All right, let's just try to reset that. Aha, okay. And you're off and back on. Let's try that again. The sample space, there we go. The sample space is defined as the set of all possible outcomes of an experiment. So the sample space is the total number of outcomes. This is kind of the universal set in a sense. But really the sample space is referring to, we're going to be looking at it more numerically. An event, so the sample space would be all the outcomes that could happen. So there could be a whole bunch of things going on, and the sample space would be the realm in which all of these things may occur. And an event would be one of those individual things. So the most simplistic example, if you have, I don't know, if you have a common example that is used are the M&Ms with the different colors. The sample space would be all the different colors. I don't eat M&Ms, I'm guessing it's like red, blue, and I think there's a brown one. That would be, all those colors together would be the sample space, and an event would be one of the single colors. And with these probabilities, we tend to look at probabilities as a number between 0 and 1. So this is when we look at these probabilities as a proportion. Normally, we take a proportion and we interpret it as a percentage. So 0.5 would be 50%, or 0.25 would be 25%. But generally, when we're dealing with ratios, the number that's most naturally going to arise is the proportion. So that's why we're going to focus mainly on this restriction of values. So we're going to be dealing with numbers between 0 and 1. If you do not get a number between 0 and 1 in this section, there's a good chance you probably did something wrong. And additionally, if you add up all the probabilities of every individual event, then you're going to get 1. It's basically saying that when you have the probability of drawing a brown M&M, a red M&M, a blue one, and you add all those probabilities together, this is the total number of potential outcomes that can happen. So these are just two properties of probabilities, that you always have to have a probability in between 0 and 1, and the sum of all the probabilities has to be 1, which immediately leads directly into example 1. So a store carries 4 brands of CD players, and they're just denoted by symbols J, G, P, and S. And they call it relative frequency. So they found the pretty much a list of probabilities of people buying one of these brands over the other 3. And A, B, and C, as it's notated here, just representing 3 different collections of information. And we're trying to see which one of these listings of probability cannot be correct. So two of the 3 are not correct, and we're going to figure out which ones are not correct and why. So as I look at all of these, one thing that immediately catches my attention is this value right here in the listing in C. Probability cannot be negative. So C cannot be an adequate listing. And what this is saying, so basically the way we would interpret that is there's a negative 26% chance of that thing occurring. That doesn't make any sense. We cannot have negative probability. So that's for part C. Now that just leaves us with A and B. And so we're also going to reject another one of these. Now the way we know which one to reject, well, all the numbers look positive, so that part's good. All the numbers seem like they're less than 1, that also seems fine. But another property, all of those probabilities have to add up to equal 1. If one of these listings do not have the sum of the values to be 1, that's a problem. So if we simply add the values in the listing together, then we can figure out which one is which. So let's pull up the calculator. So I'll start with the first list, list A. 0.20 plus 0.07 plus 0.24 plus 0.64. Yikes, we get a number that's larger than 1. So it instantly cannot be A either, because the sum of the probabilities actually I should put must equal 1. And as we saw, the sum of the probabilities came out to be 1.15. So what about part B? If Part B, same idea. We can add up all the numbers in the list, 0.37 plus 0.3 plus 0.19 plus 0.14. That's perfectly 1. We can accept answer choice B. All of the probabilities are within 0 and 1 inclusive, and the sum of all of them is equal to 1. So primarily that example is just testing your interpretation or the definition of a probability. The scope of the probabilities and the sum of the probabilities to equal 1. So that's primarily definition oriented, but let's get into the real type of probability-based problems and the strategies we would use for determining probability. The probability of an event in its most formal explanation. So if you have a sample space of all of these different occurrences and you want to figure out the number or the probability of one of the occurrences or one event, which could be a combination of occurrences within the sample space, the probability, which is denoted, normally we use a capital P in front of an E. E represents event, the specific event, and P is the probability. Notice that this number breaks down to the number of elements in an event divided by the number of elements in the sample space. In other words, this is 2 counting problems. That's what this comes down to. So the previous section we did on counting, this whole section is basically 2 counting problems altogether. So that's how this section continues from the previous section. It's basically twice as much work, but there's going to be an overlap in the 2 counting problems that we do. So it's not entirely twice as much work. But let's go ahead and look at what I mean by this. So that means we're counting. So that means we need to think about counting methods. Or if we already know the numbers, then just need to accumulate them appropriately. So add example 2. A cooler at a picnic contains 100 cans of soda. There's 25 cans of cola, 45 cans of orange soda, 24 cans of ginger ale, 6 cans of root beer. And if one can is selected at random, determine the probability that the soda is ginger ale, orange soda, or root beer. Okay, so that's a lot of information. This is a paragraph throwing a bunch of numbers at us. So remember in the last section, the primary sequence of steps was determine the number of dashes, what numbers go into the dashes, does order matter or not. I'm going to try and break down this section as another sequence of steps. It's going to be a little bit different, of course. Really, the way I'm going to start off all of these, we're going to be looking for the probability of some event in each problem, which means we need to know the number of elements in that event divided by the total number of outcomes. I will be starting off every problem with this notation. It's just a formality. So that means we sort of need to decipher 2 different counting ideas. So kind of off to the side, we need to figure out the number of elements in the event and the number of elements in the sample space. So like I said, it's 2 separate counting problems. So the first thing we want are the number of elements in the event. That means we need to know what the event is. The event that we're trying to figure out, well, it says determine the probability that the soda selected is ginger ale, orange soda, or root beer. That's the event. Ginger ale, orange soda, or root beer. That's what we're trying to determine the probability of. So we need to figure out the number of options for ginger ale, orange soda, or root beer. Well, if we look up above at the problem, Ginger ale is right here. So started off with 24. Orange soda, 45. And the last one, what's the last one? Well, root beer. So 6 cans of root beer. Do we multiply these numbers together or add them? Do you have any intuition? Is this an addition principle or a multiplication principle?
Addition.
Well, this is going to be addition. So this one's addition. So this one's addition. We're basically seeing the total number of options available. So we would use the multiplication principle if there were, so this problem only states that one can is selected. So that one can would be the only position. So there's nothing else to multiply. You might think, what about the ginger ale, the cans of orange soda, and the 6 cans of root beer? It's not saying you're picking 3 cans from each one of those. It's saying you're picking 1 can, and that's your total number of options. So that's why we're adding in this case, not multiplying. We're only picking 1 can, which means it's one number. And so 24 plus 45 plus 6, what is that, 75? So that's the first part. So we'll call that part A, why not? Then part B, a little bit more room. And so now B, or the number of elements in the sample space, this is, well, in this context, this is the total number of cans in the whole entire problem. And it does say at the very beginning, there's 100 cans in total. So there's nothing really to count. There's 100 cans in total. So in essence, what we truly have, we found 75 as the numerator value, 100 as the denominator value. This comes out to be 0.75. So in other words, the way we would interpret this as humans would be, there's a 75% chance of selecting ginger ale, orange soda, or root beer. And another way to know that you shouldn't have multiplied the numbers together in part A, your fraction would come out to be a number much larger than 1, and you cannot have a probability that's larger than 1. So that would instantly tell you, I did something wrong. You should always have numbers in between 0 and 1, inclusive. You can have 0, you can have 1 as well. Does anyone have any questions about this? Yes?
Should we always keep it as a decimal, or do you want us to change it?
So sometimes it depends on how my math lab asks for the answer, because as you know, my math lab is picky and somewhat random at times. Generally, proportions are the most commonly used, but don't be surprised if they do throw in, express your answer as a percent in that little blue annoying text right after the answer. They might shove that in somewhere, but generally, and on the midterm, it doesn't matter either way. I'm going to grade it correct either way. But for the most part, we like to keep these as proportions, as decimals. Any other questions before we move on? So this is kind of the idea. And so we haven't really done counting using the multiplication principle quite yet. Really, we use the addition principle when we're only selecting one object. What about if we select 2 or more objects when a multiplication is necessary? Well, let's look down at example 3. A town council has 14 members, 6 Democrats and 8 Republicans. President and vice president are selected at random. What is the probability that they are both Democrats? Now, something I unfortunately couldn't obtain was a book that I own that's over 100 years old, a math book from maybe 1900, and it has this exact problem in it. I thought that would have been cool to bring, but I couldn't find it anywhere. Somewhere in my office, just cannot find it. But this exact problem's in there, so mathematicians aren't really too original. Can't think of a new problem after 100 years, but anyways, there's 14 members, 6 Democrats, 8 Republicans. If the president and vice president are selected at random, what is the probability that they are both Democrats? Now, as I mentioned, I'm going to start off with this notation. It's just a formality. Just going to get acclimated to using this notation, which means I'm going to be considering 2 things off to the side. The number of elements of the event and the number of elements of the sample space. This is pretty much our off to the side scratch work, in other words. So the first thing we need to do is figure out the number, well, really we need to figure out the event first. So the event in this case, well, does anyone happen to see the event? Yes. What's that?
Is it 14?
So even before we get to the number, what's the event, just in words? Like, what are they asking us to find?
Really, they are both Democrats?
So that they are both Democrats. So you selected the right phrase. So that's the event, that they are both Democrats, which implies, both implies 2. So the event is choosing 2 Democrats. That's the event. And if you want to start writing that off to the side, that actually may be a good idea. The event here is equivalent to really just picking 2 Democrats. Just in layman terms, that is the event. And so now we need to figure out the number, we need to count the number of outcomes for which we can select 2 Democrats. Since we're choosing 2 or more things, we're using the multiplication principle. In other words, we're going to use the methods we did in the last section, primarily in the last section, which means the dashes, the number in the dashes, and so on. So we're picking 2 Democrats, which means 1, 2. And this is how the previous section is coming back into play. And this is the multiplication principle, since we're picking 2 or more. The next question is, what are the numbers that go into the spaces?
8.
What's that?
I said 6 and 8, but I don't know.
So it's not going to be 6 and 8 because this event is only concerned about Democrats. So we have 14 members in total, that's true, but this is asking about just Democrats, which means not all 14, but just the 6 Democrats. Now we're selecting from a smaller space.
6 and 5.
It's 6 and 5, yes, it's 6 and 5. There's 6. So notice also they didn't say anything about repetition, but we knew instinctively, well, you can't repeat people. So you're choosing one of the 6 Democrats, and then, well, you have to choose another one. So it's down to 5. Does order matter or not? Well, here's where it gets a little bit easier. It doesn't matter if order or not, all right, let me try that again. It does not matter if order matters or not in this section. This is a step you get to skip entirely. You are not dividing in this section. I mean, you can keep the dashes for the spaces. Or in other words, you're always dividing by ones when you do probability. There's a mathematical reason why this is the case. Technically, if you divide by, if order doesn't matter in the numerator, order is not going to matter in the denominator for the sample space, and those two values end up canceling out every time. If you don't care about the mathematical jargon behind it, then just assume order always matters in this section and always divide by ones. That is unique for this section. This is not true for the previous section. For this section, this is basically a shortcut that I'm giving everybody. So we do not care about the order in this section. Do not care about it. So I put ones here. Actually, what I'm just going to do is erase them because, I don't know, I feel like it's going to throw me off. And 6 times 5 is 30. And so that's the number of ways in which a Democrat can be chosen. Now, the number in the sample space, so that quantity on the right, so of course we just figured out the numerator. We're just going to leave a blank for the denominator. So the number of people in the sample space, so what is the sample space? Not the number, but what is the sample space in words? What's that? Well, it's you said members? Okay, yeah, perfect. Yeah, it's the members. But not just the members as a noun, how many members? 2 members. What the sample space is saying is remove all the restrictions. All I care about are the 2 people chosen in general. So the sample space will always remove all the restrictions because we're looking for the total number of occurrences. Whether it's Republican or Democrat, it doesn't matter. Just the total number of occurrences. So you're still choosing 2 people. And normally the number of dashes is going to be the same. This is normal, unless they just, sometimes they might give you this number, but actually not in this context, never mind. But yeah, normally the number of dashes will be the same. And now we're not choosing from the 6 Democrats anymore. We're choosing from all 14 now. All 14, no restrictions at all. So now it's 14, any one of the 14 people, regardless of political affiliation, and then the 13 because we can't repeat. And so 14 times 13, now it's probably a reasonably large number, 182. Cool. So that's how many choices in general, regardless of restriction or event, which tells us the denominator. And so now we have a quotient, 30 divided by 182. My math lab could ask for 2 decimal places, 3 or 4. I'm going to put 0.1648. I'll round it to 4 decimal places. Again, it might ask for more, it might ask for less, or it might ask you to convert this to a percentage, which means you simply multiply the result by 100, or move the decimal place to the right 2 times. But in any case, this is telling us the proportion of 2 Democrats being chosen relative to just 2 people being chosen. Or in other words, there's a 16.48% chance of 2 Democrats being chosen. Does anyone have any questions before we look at just more examples? Oops. Okay. All right, this example 4 may look familiar, except now it's just 1 less wheel. It's 3 wheels now. Still the same situation as we saw in the previous section though, 10 digits from 0 to 9. If an opening combination is a particular sequence of 3 digits with no repeats, what's the probability of a person guessing the right combination? So it's not so in the previous section, the way they worded it was the number of combinations possible. Here they're asking for the probability of guessing the right combination. This problem may be a little bit tricky if you overthink it. So here, again, I'm going to start off with this notation here. And I guess we'll go ahead and just throw in what the event logically means. Not the number, but just the event, what that is referring to. What is the event in this problem?
One person gets in the right combination.
So the event is going to be, we'll trim that down a little bit, the right combination. The right combination, or the correct combination. So if anything that might help us visualize, so as we do this off to the side, the number of times that this event can happen versus the number of elements in the sample space. The event is the correct combination. How many times can that happen? One time. Once. There's no multiplication in this part. This is one of those situations where if you overthink it, you're probably going to get it wrong. But there's only one way to guess the correct combination. So don't be too tripped up by that one. There's no multiplication principle in that one. But for the number in the sample space, this is going to be, so we're removing any restrictions. So there's no longer any right combination or wrong combination. Now it's just the number of combinations in total. So how many things are we choosing? 3 wheels, 3 spaces. Three wheels, so 3 spaces. And then we figure out the numbers that go into the spaces. Well, the first wheel can be any one of the 10 digits. And then what follows after that? It would be that. Notice what they snuck in. No repeats. They snuck it right in there. So 9 and 8. I believe that's 720, right? 9 times 8 is 72, and then you just throw a 0 behind it. 10 times 9 times 8. So really, this is 1 divided by 720. So you have a 1 out of 720 chance of guessing this correctly. So this 0.001, I'll do 139. Again, it might ask you to round to a different amount of decimal places, or it might ask you to convert this to a percentage. I'll just represent the answer as a proportion rounded to 5 decimal places. So if we were to interpret this, there is a 0.139% chance of guessing it right on your first try. So it's not even 1% chance. It's a it's a 0.1% chance of guessing it right. And that's only for 3 wheels. If there were 4 wheels, it'd be a lot worse. Does anyone have any questions about this before we move on? Let's move down to example 5, which almost looks like a problem from the very beginning section of this chapter. But refer to the Venn diagram. So it's already filled out for us. So it's not necessarily a sets problem. But notice for parts 1, 2, and 3, there's P in front, not an N, but a P in front, which means they want the probability. And so with each one of these, so remember that notation I was using, and I'll kind of scroll up to show you that notation I was using. The one all the way up here. I was doing that first. The way I'm going to modify it for this problem, the number of elements in whatever that inside set is, divided by the number of elements really in total. So notice wherever the E is at, that set pops up as the first number we're trying to find. Since they replaced that set, or they specified the set, then I'm just going to go along with what they say. So what we have to do is, well, first we need to figure out the number of elements in the complement of A. Remember that the apostrophe means the complement, or in other words, everything not in A. So let's see, we need to remember then some set theory. What does that mean to not be an A? Well, for starters, here's A. So that means these 2 numbers are in A. But wait, I changed my mind. Now I want things not in A. So what did I not underline? 20 and the 25. Those are the things not in A. So really, it's the 20 plus the 25. This is an addition rule. We're not multiplying the 2 together. We're not choosing various options. And then we divide that by the number in the sample space. Or in other words, if we remove all the restrictions, what's the total number of options? The total number of options, well, that's just all the numbers added together. 45, 10, 20, 25. So that's 45 divided by, let's see, that's 55, 60, 75, 100. Which just comes out to be 0.45. So this is how we apply this when we're given a Venn diagram. A completed Venn diagram at that, so it makes it a little bit easier. The next thing we need to find, remember what that U means. That's the union. Which means or. Everything in A or B. So if it appears in A or B, we include it. What are the numbers that are included in A or B? Yeah, the 45, the 10, and the 20. Any number that appears in either the set A or the set B. So that's those 3 numbers. So the formal notation, whatever the set name is that they gave us, I'm just rewriting it as a number, still divided by the number of total elements. So we figured out the union consists of 45 plus 10 plus 20. The total number of elements, well, that's not going to change. Still 100. Still the total number of elements. So I'm just going to put 100 again, but really it's the 45 plus 10 plus 20 plus 25 again. So what is that? 55, 65, 75. So it's just 0.75. So there's 75% of selecting an element from either A or B. So the last part seems pretty interesting. Well, if anything, the notation, we just borrow the symbolism. So that would be the symbolism, and now we need to figure out what the numerator is going to look like. And well, we already know what the denominator is going to be. That's still going to be 100. But what is that? The complement of A intersection B. Complement of A intersection B. Now to figure out the complement, it's always good to start off with, well, the regular set itself, and then we can complement it. So what is A intersection B? The intersection is and. That's the overlap. So 10 is the only number in that shaded region. That's just the intersection by itself, nothing to do with complements yet. That's just A intersect B, or A and B. The complement says, okay, I changed my mind. I don't want that one. I want all the other ones instead. So what did I not underline? 45, the 20, and the 25. That's going to be the three numbers I add together. So the 45 plus 20 plus 25 divided by the total number of elements or outcomes. It's 100. And working backwards, I believe this is going to be 90 divided by 100, which is 0.9. Does anyone have any questions up to this point? Okay, let's move on to example 6. Now for these problems, we're going to be referencing a standard 52 card deck of playing cards. If you're not familiar with how playing cards are, well, just what the numbers are and the suits and all that, I did add, depending on what time you printed out the notes, you might not have this, but the newest notes online has this appendix with information about the 52 playing cards and the rolling 2 dice outcomes, which we'll talk about later. But basically with a deck of cards, if you're not familiar, there's 4 different types of symbols called suits. There's clubs, spades, hearts, and diamonds, each one being 13 apiece. So basically 52 divided by 4. And half of the cards are black cards, which would be 26. Half of them are red cards, which is 26. So if they say anything about a suit, that's just referring to the symbols, the clubs, spades, hearts, and diamonds. So you might see some of this terminology pop up. And if so, hopefully this diagram might be comprehensive in terms of explaining how the numbers work. So we're going to go back and forth between this diagram as we answer some questions about probability pertaining to this. This is stuff that probably gamblers are very much oriented with. They like to figure out probabilities of various things. In fact, you can use this stuff to determine the probability of getting if you're familiar with Texas Hold'em rules, a full house or a flush or straight, things like this. So the premise is there's a 52 card deck of playing cards. Suppose we draw one card. Okay, so let's visualize that. We draw one card. And well, actually, that's kind of redundant because it just says it right there. Yeah, that's redundant. Oh well. Suppose we draw one card. What's the probability of drawing a spade? All right, so what's a spade? I thought we were talking about playing cards. A spade is one of those symbols on the playing cards. Yeah, there's 13 of them, exactly. So if we scroll down here, so what did it say, a spade? Yeah, so it said a spade. So I'll leave the spade one circled. So if you see, if it says spades, clubs, hearts, or diamonds, it's referring to a suit. And so as we see here, it's 13 spades. So let's keep that number in mind. There's 13 spades. I'm going to scroll back up. So off to the side, a spade, just say 13 spades, just to remind us. So this is a probability problem, which instantly means that I'm looking for the probability of some event. And notice since they didn't give us a symbol like in the previous problem, I just default to using E, which means we need to figure out the number of elements in that event divided by the number of total outcomes. So maybe I can fit this over here. So the first question we need to ask is, what's the event that we're looking for? What's the event, just in words? Not just, well, I guess a spade. I guess that does answer the question. We're drawing, the event is just drawing one spade. That's the event. So the event is drawing one spade. So how many options do we have for that one spade? It's 13. If we chose more cards, we would multiply blah, 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 but we're only drawing one card, so that's why it's just 13. So that gives us the numerator over here. Now the sample says, ignore the stuff about spades, it's too specific. Now we're just drawing a regular card. How many options do we have? It's the 52. Now it's saying no more talk about spades, just no restrictions at all. 52. So naturally, of course, that's going to just be 0.25 because spades are a fourth of a deck of playing cards. So that kind of makes sense intuitively. We have a 25% chance of drawing something that takes up 25% of the deck. Oh, that's the first part. The second part might get a little bit more complicated. We're drawing one card again. What's the probability of drawing a red card or a 4? A red card or a 4. Let's remember that phrasing. We'll come back to this. Let's go to our diagram. A red card or a 4. So how many cards or what quantity would that be associated with? A red card or a 4? So that's the answer everyone normally gives. And there's just one caveat to that. So there's 26 red cards.
28.
It's 28, yes. I'll explain why momentarily. There's this overlap. So there's 26 red cards, and there's what did it say? A red card or a 4? Is that a 4? Okay. So it was a red card or a 4. Well, a lot of people say, all right, if there's 26 red cards and 4 4s, then that's 30 cards in total. But what you're not, or what these people are not considering is that there's overlap here. You're counting these 2 cards twice, and you don't want to count them twice. So really what we're doing is counting every card here. So that's 1, 2, and then the 26 red cards in total. 3, 4, blah, 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 blah. It's 28. That is 28 cards that are either red or a 4, not 30. It's not 40, it's 28. So let's see if we section this off. 28 cards, just to keep that number in mind. There's 28 cards that are either red or a 4, not 30. Or technically, well, not technically, wrong choice of words. There is a formula we actually learned that sort of explains this as well. I'm going to erase this almost immediately, so don't write this. So the union is equal to adding the 2 sets together minus the intersection. We found that there were 26 red cards plus 4 4s, but we subtracted off what they had in common. There's two 4s that are red, and that's why it's 28. So just to sort of connect all of this together, that's probably one of the first practical uses of that formula. But again, that's just food for thought, more so than anything. Instead, what we care about is the formal jargon. The probability is equal to this. And now we need to figure out the number of cards in the event, the number of possible options for the event, and the options we have, the total number of options. So the event in words is, what is that again? So this is without the number, so no mention of 28 quite yet, just the wording. What are we looking for? If I asked you, what are we looking for in this problem? This is, yes, I'm drawing 1 red card or 4. That would be in wording the most stripped down way of looking at the question here, drawing 1 red card or 4. So the number of different cards that are possible to draw this, that's the 28. We're drawing 1 card, and we're hoping that that's a red card or 4, which means 1 card, which that tells, ultimately that's telling us the number of spaces, in other words, or number of dashes. And the red card or 4 as the restriction is telling us the number of possibilities we have. And then the total number of possibilities is still the 52. Because we're still choosing 1 card, and the total number of cards in the deck is the 52. So this is 28 divided by 52. It's probably going to be a number a little bit over 0.5. So let's find out what that is. 28 divided by 52. 0.53, say 85. Why not? 4 decimal places. Okay. And let's look at the last part. So now we're drawing 4 cards, not 1 card, 4 cards. What is the probability of drawing 4 hearts? Yeah, we're talking about cards. What's this hearts thing all about? Hearts is one of the suits. So 4 cards, what's the probability of drawing 4 hearts? Let's figure out the number of hearts first. So if we scroll down here, it says that there's 13 hearts. So, okay, that was easy. It's 13 hearts. So let's keep that number in mind as we scroll up. So off to the side, I'll just put 13 hearts. So we're looking for some probability. We need to figure out the number of elements in the event divided by the number in the sample. Let's start off with the number of elements in the event. What is the event itself in this problem? It's 4 hearts. Not 1 heart, it's 4 hearts. So what is that going to imply about our first step?
You can like draw 4 dashes.
4 dashes, that is correct. 4 dashes. So I wanted to distinguish that from the previous 2. There's 4 dashes now. We're drawing 4 cards. 4 cards. So now we ask ourselves, well, what numbers go into the dashes? So the event, the context of the event is, well, the 4 told us the number of dashes, and the hearts tells us pretty much the smaller subsection that we have to look at. How many cards do we get to choose from? It's 13. So you have 13 options for the first card. You pick that one up. Okay, cool, I got a heart. So the next card you pick up, you have 12 options. You lose 1 because cards cannot repeat. So you have 12, and then 11, and then 10. Now, with that, we need to figure out the total number, well, the number in total, the total number of options. So we ask ourselves, okay, how many dashes do we draw? We're still drawing 4 cards. We're drawing 4 cards. The only restriction is that instead of 4 hearts, it's just 4 cards. Like I said, the majority of the problems, we saw one earlier with the right combination that didn't have this characteristic, but generally, generally you're going to have the same number of dashes between the number in the event and the number and the sample space. There are some situations where this doesn't happen, but the majority of the time, this should be expected. So we're not choosing from the restriction of hearts anymore. Now we're just drawing any card now, which means we have more options. In fact, we have 52 options for the first card, and then 51 options for the next one, 50 and 49, because we still cannot repeat. And again, it does not matter in this section whether order matters or not. So I am just not writing it down. It does not matter. Well, order just does not matter at all. So we never have to divide by anything in the specific sections. Again, for a reason that might be a little bit more algebraic than necessary to explain. So instead, I'll go ahead and solve these 2 numbers right fast, and then put them all together at the end. So 13 times 12 times 11 times 10, 17, 160. And then the next one, 52 times 51 times 50 times 49. I should have given myself a little bit more room here. give myself a little bit more room here. So 52 times 51 times 50 times 49. 649740. There we go. It's a little better. So now I know what to put in the numerator. Now I know what to put in the denominator. And all together, we can throw that into the calculator. 17160 divided by really the last 17160 divided by answer. And so we get 0.00264. That seems fine. So there is a 0.264% chance of drawing 4 hearts from a deck. That is 0.2%. So it's very unlikely. Does anyone have any questions about that? So what I want to do now, so I figured I can start up on example 7 next week. And I wanted to spend the remainder of class time while asking if anyone had any questions from the counting section, from the homework. So this probability homework, this homework's not due yet. There might be a due date in my math lab. You can work on it if you want. But since the counting homework is due tonight, I wanted to ask if anyone had any questions, and if not, I wanted to do some of the ones that might be a little bit more difficult. Or I can work on the workbook pages, the remainder of them.
Adam, can you do the first one in the homework, like the first question? I think I wasn't here that day or something.
From here or the other?
From there.
Okay. The very first one.
Yeah, that.
So let's see. So the college offers 2 introductory courses and history. Okay, so you don't want to overthink this one. So it's 2 courses in history, 1 in science, 2 in math, 3 in philosophy, 4 in English. So a bunch of different choices. And remember, this is counting, so let's try to divert our focus from probability-related steps back to the dashes. Most of the problems are dashes, numbers in the dashes, and we're back to wondering if order matters or not. So ultimately what we're thinking about here is for each course, so there's a history one, there's a science one, there's a math one, philosophy, and English. How many options do we have for each? 2, 1, 2, 3, 4. And they're all being multiplied. Order would matter in this situation because, so I think when I first taught this, I mentioned that really order does matter whenever one of the indications is if each individual position can be labeled. That was one of the ways I explained it when we first started looking at some of these. So we divide by ones because order matters. So really this is 2 times 2 is 4. With that 4, that's 16. 16 times 3 is 48, which is what part A is. Part B says if a part-time student can afford to take only 1 introductory course, how many selections are possible? So I think part A might have been a little bit easier. What about part B? How many dashes would we put for part B? 1. You're taking one course instead of a course in each, which was 5 in total. Only one course means 1 dash. What number would go into that dash?
5.
So that's not 5. That's the total number of courses available. There's 5 courses available, but that's not the total number of selections.
Well, 28.
It's the addition of all the possible courses here. It's the addition. So I can either choose from one of these 2 history classes, or I could pick a science, or I could pick one of these 2 math classes, or one of these 3 philosophies, or one of these 4 Englishes. And whether order matters or not, it's still just one selection. So in either case, you're going to be dividing by 1. So 2 plus 1, that's 3, 6, 7, 8, 12. Is any one of the 12? Oops, go back to that. Does anyone have any questions about this one, or any problem you might want me to work out? Or if not, I can go find one.
What was the one with the graph stuff on
Is it called a tree diagram?
it? Yeah.
Tree diagram. Tree diagram. Let's look at the tree diagram. That sounds kind of interesting. I wonder if that's towards the end. Tree. Oh, the tree. Okay. I don't like the tree one too much. Okay. I forgot all about the tree one. Okay. Let's talk about it here. So, how many 4-letter code words can be formed from the first 4 letters of the alphabet? The tree diagram is basically a way of organizing all the potential options that you can have. So if no letter can be used more than once, so there's 4 letters, so your 4 spaces would correspond to each column of your tree, which already tells us the answer. The first space can be either A, B, C, or D. The second space is going to be based off of whatever your first choice is. So if you pick A for the first one, then you have B, C, or D for the second one. Your third column is the next space, and your fourth one is, of course, the fourth space. This choice over here on the right says that you would only pick 2 letters, but we're choosing 4. This one says, I don't even really know what it's saying. It's just, I guess it's only saying you're picking 1 letter, and they're throwing E and F in there for some reason. So that one definitely can't be right. And then the last one says you're only picking 3 letters. Oops. So the last one's saying you're only picking 3, so that can't be right either. We're picking 4, which means there would be 4 columns in our tree diagram. Yeah, I'll look at number 2 momentarily. So now it's saying using the multiplication principle. Now this is going back to something a little bit more familiar. With the multiplication principle, what is the number of 4-letter words that can be formed? So we already determined there's 4 dashes. 1, 2, 3, 4. Now how many options do we have? 4-letter code words. We only get to choose from the first 4 letters of the alphabet. So we start off with any one of the 4, but it says we can't repeat. So we go down to 3, then 2, then 1 to get 24. Is that help people a little bit more. I forgot all about the tree diagram one. Yeah, hopefully that makes it a little bit more clear. If it doesn't make too much sense, hopefully the ease of the process of elimination will at least make it tolerable. So I had a request for problem 2. Let's see, is there any more tree ones? Nah. So I had a request for 2. And I'm going to push off 2 as a problem we did in class. I did see your email about that. I'm going to go ahead and email you for the virtual person who asked that. I'm going to email you back more information on this one, if that's all right. I'm going to focus on ones I didn't do in class. But just to acknowledge, I did see your email. So let's see. Any other suggestions for problems, or should I just find a kind of brutal one? That one might just be a combination one. It's another just straightforward combination. Same thing. I think 32 might be tricky because it uses a symbol that we haven't really used too much in this class. It means if A is a subset of B. So basically, everything that happens in A is part of this much larger circle that is B. So A is sort of trapped in B. So think about it that way. And it's saying in our Venn diagram over here, which I'll go ahead and write again, just a little bit larger. It says X, Y, Z, or W. It's saying which one of those has to be 0 if A is truly just trapped in B. Now, this diagram is very generalized, so it may not seem clear which one it is. So if we were to rewrite this diagram over here on the left, B would be a larger circle, and A would be some tiny little part inside of it. If we simplified that diagram, in other words. So really, the way this changes the diagram is that A, so remember this one's A and this one's B, A no longer has anything unique to itself. X is going to be the one that's 0. And the reason why is because what this over here represents is everything that A has that B does not. But if A is trapped in B entirely, that means A has nothing unique. Everything in A has to be a part of its bigger set B. That's why X would have to be 0 in this case. That one's kind of a tricky one. Maybe I can get in one more. I know I did 30. Let's see, maybe I can do one more problem. No. I know we did this one in class. Now it's just multiplying. I don't know, how's everyone feel about this? I have 1 minute left. Each one of the children, I'll just go through this one real quick. So 25, each of the children will be allowed to select 1 box of cereal from the 12 different boxes available. How many selections could be made? Well, how many selections are happening in this problem?
3.
It's 3. Each child selects their own. What are they choosing from? 12 different boxes. Can we repeat?
No.
Can't have 2 of the same. 11 and 10. Twelve times 11 times 10. We'll just put 1320. Oh wait, forgot about checking order. order matters, which didn't really change the problem, but that's why you put ones here. Order matters. Which seems kind of strange to me, but I guess every child has their own specific serial to theirs. 1320. Okay, I'm out of time. So again, this homework is due tonight. Quiz is due Friday. Workbook is due Friday. Other than that, that's all I have. Have a good day.